Tonight, you are going to learn something about the solar system that the diagrams in every textbook, every classroom poster, every animated explainer you have ever seen quietly left out. Not because it was a secret, not because the science was uncertain, but because the truth, drawn to scale, would not fit on any page ever made. The solar system, the one you were shown, with its 8 planets arranged in neat rings around a yellow sun, ends somewhere around Neptune, if you learned it the way most people did. But Neptune is not the edge. Neptune is barely the beginning. The real solar system extends so far beyond that familiar picture that our fastest spacecraft, launched decades ago, would need longer than all of recorded human history to reach it. If you enjoy spending quiet hours with the deep science of space, take a moment to like this video and subscribe to the channel. It helps more than you might think, and it means we can keep making these. Now make yourself comfortable. Let's begin. There is a version of the solar system that lives in the human imagination, and it is a reasonable version. It was built from what we could see, from what our instruments could confirm, from the long and careful work of astronomers who spent lifetimes mapping the sky one careful degree at a time. In that version, the solar system has a shape. It has a center, the sun, bright and enormous and warm. It has a middle, the 4 rocky planets close in, then the asteroid belt like a thin river of rubble, then the 4 giants floating farther out in the cold. And it has an edge, a place where the solar system stops and space begins. For most of the 20th century, that edge was Pluto. Discovered in 1930 by a young astronomer named Clyde Tombaugh, working at the Lowell Observatory in Arizona, Pluto sat at the far margin of the known solar system for decades. At nearly 40 astronomical units from the sun, 40 times the distance between Earth and the sun, it felt remote enough to be final. This was the frontier. Beyond Pluto, the thinking went, was simply the void. That picture held for a long time. It was comfortable and it was wrong. And it was wrong in the particular way that many comfortable pictures are wrong. Not in the details, but in the scale. We now know that Pluto is not at the edge of the solar system. Pluto is not even close to the edge of the solar system. Pluto is a near neighbor. Pluto is practically inside the house. In 2006, astronomers reclassified Pluto as a dwarf planet, partly because by then, it had become clear that it was not an anomaly at the solar system's edge. It was one of thousands of similar objects in a broad disk of frozen bodies extending beyond Neptune's orbit. That disk, called the Kuiper Belt, stretches from roughly 30 to 50 astronomical units from the sun. It contains hundreds of thousands of objects larger than 100 kilometers across, and millions more smaller than that. It is large and it is cold. And for a while it seemed like it might be the true outer structure of the solar system. It is not. But before we reach what lies beyond the Kuiper Belt, it is worth pausing on a milestone that felt, for a brief moment, like an ending. On September 12, 2013, NASA announced that Voyager 1 had done something no human-made object had ever done. It had crossed the heliopause. The heliopause is the boundary where the solar wind, the constant stream of charged particles flowing outward from the sun, finally meets the interstellar medium and gives way. Inside the heliopause, space is filled with the sun's own breath. Outside, you are in the interstellar medium proper, the thin gas and ancient radiation that fills the space between stars. Voyager 1, launched in 1977 and traveling for 36 years, had finally crossed that threshold. The headlines called it leaving the solar system. NASA called it entering interstellar space. It was a remarkable achievement. It still is. But there was a quiet inaccuracy buried in how the moment was described. The heliopause is not the edge of the solar system. To understand why, you have to understand that the sun casts 2 kinds of influence outward into space, and they are not the same thing. The first is the solar wind, the stream of charged particles, the plasma, the radiation pressure that inflates a great bubble around the sun called the heliosphere. Voyager crossed the outer wall of that bubble. That is what the heliopause marks, the edge of the sun's breath. The second kind of influence is gravity, and gravity is something different entirely. Gravity does not blow outward like a wind. It does not thin out and stop at a surface. It reaches. It reaches far beyond the solar wind, far beyond the heliopause, far beyond anything Voyager 1 has yet approached. The sun's gravitational influence does not end at the heliopause. It does not end at the Kuiper Belt. It does not end anywhere near where the diagrams say it ends. When Voyager 1 crossed the heliopause in 2013, it was approximately 121 astronomical units from the sun. By the time this video was made, it had traveled to around 160 astronomical units, roughly 14.9 billion miles from home. At its current speed of about 38,000 miles per hour, it is the fastest human-made object ever sent into space. It has been traveling for nearly 5 decades, and it has not yet reached the edge of the solar system, not even close. The sun's gravitational influence, the region within which objects are genuinely bound to the sun, orbiting it, belonging to it in the way the Earth belongs to it, extends somewhere between 50,000 and 200,000 astronomical units from the sun. At Voyager's current speed, reaching the inner boundary of that region would take roughly 300 years. Passing through it entirely could take 30,000 years or more. This is what was left out of the poster on the classroom wall. Not as a deception, simply because the truth would have required a canvas the size of a city. The distinction between where the sun's breath ends and where the sun's gravity ends is not a minor technical detail. It is the difference between a solar system that fits in the imagination and a solar system that does not. Most people, when they think of the sun's domain, are thinking of the heliosphere, the warm lit region, the place where the solar wind still blows, the space that Voyager finally exited after 36 years of travel. But the sun's gravity holds something much farther out, something ancient and enormous and almost entirely invisible, something that was inferred before it was ever searched for and has never been directly observed to this day. It was Voyager's crossing of the heliopause that made the contrast clearest. Here was our greatest achievement of distance, a machine that had traveled farther than anything we had ever made, crossing a boundary that felt cosmic in its remoteness, and it had barely scratched the surface of the solar system's true extent. The heliopause sits at 120 astronomical units. The structure waiting beyond it begins at 2,000 and does not end until perhaps 200,000. What lies out there, what hangs in the cold and the dark at distances the mind genuinely struggles to process, is what this video is about. And reaching it in the imagination requires us to first sit with the strangeness of where the familiar ends. Because the familiar, as it turns out, ends very close to home. Neptune, at 30 astronomical units, is close. The Kuiper Belt, ending at 50, is close. Even the heliopause at 120 is close. Close in the way that the nearest town is close when you are about to cross an ocean. Beyond 120 astronomical units, Voyager travels on in silence. No solar wind fills the space around it anymore. The interstellar medium thins the gap between stars. The sun, behind it, has dimmed to a point of light, still the brightest star in Voyager's sky, but only barely. And ahead, and above, and below, and in every direction, the sun's gravity still reaches, still holds, still shapes the slow orbits of things we have never seen and may never see. That region, that vast, dark, gravitationally bound shell surrounding the sun on every side, is where we are going next. The man who first gave shape to what lies beyond the Kuiper Belt was not working from a telescope. He was working from a pattern, a quiet, persistent, statistically improbable pattern that hid inside the orbital data of comets, those brief, luminous visitors that have crossed human skies since before writing existed, inspiring wonder and dread in equal measure across every civilization that ever looked upward. His name was Jan Hendrik Oort, a Dutch astronomer born in 1900 who spent much of his career at Leiden Observatory in the Netherlands. Oort was a careful and systematic thinker, the kind of scientist who finds meaning not in the spectacular object, but in what a large collection of ordinary objects quietly implies. And in 1950, examining the known orbits of long-period comets, he noticed something that should not have been there. Long-period comets, comets with orbital periods longer than 200 years, some of them taking millions of years to complete a single loop around the Sun, were arriving from every direction with roughly equal frequency. Not preferentially from the plane of the solar system, where the planets and the Kuiper Belt sit, but from above and below and sideways from every angle of the sky. They came, as Oort noted, as if from a sphere, a vast, surrounding, spherical reservoir of objects distributed evenly in all directions around the Sun. No such structure had ever been proposed. No telescope had ever seen it, but the mathematics of the comets demanded it. If there were no reservoir, no distant population of icy bodies surrounding the solar system on all sides, there was simply no way to explain where these comets were coming from. A disk would produce comets preferentially from one direction, a sphere would produce them from all directions equally, and the data said sphere. Oort published his hypothesis in 1950, and the structure he proposed has carried his name ever since, the Oort Cloud. It is worth pausing on how unusual this is in the history of science. Most major structures in the solar system were discovered through observation, seen through a telescope, photographed, tracked across the sky. The Oort Cloud was inferred. It was reasoned into existence from the behavior of objects that had fallen inward from it, the way you might infer the existence of a mountain range you have never visited by noticing that all the rivers in a region flow from the same direction. The cloud itself has never been photographed. No spacecraft has ever visited it. No direct image of any Oort Cloud object has ever been taken. It exists, as of now, entirely in the mathematics and the logic of what the comets tell us. And yet, its existence is not seriously doubted. The inference is too clean, the pattern too consistent, the alternative explanations too inadequate. So what is the Oort Cloud, in physical terms? In the broadest sense, it is a vast, roughly spherical halo of frozen objects, ice, rock, organic compounds, surrounding the Sun at enormous distances. It is not a cloud in the sense of something dense or visible, or even close to being photographable. It is a cloud in the sense of a diffuse, enormous population of objects spread across a shell of space so large that the word large becomes immediately insufficient. Astronomers generally describe the Oort Cloud as having two regions, though the boundary between them is gradual rather than sharp. The inner region, sometimes called the Hills Cloud, after the astronomer Jack Hills, who proposed it in 1981, is somewhat flattened, still retaining a slight disk shape inherited from the early solar system. It begins at roughly 2,000 astronomical units from the Sun and extends to perhaps 20,000. It is thought to be denser than the outer region, containing more objects in a more compact space. Though compact here is a word that requires careful handling, we are still speaking of distances that dwarf anything in the familiar solar system. The outer region is the Oort Cloud proper, the structure Oort himself described. It begins somewhere around 20,000 astronomical units from the Sun and extends outward to perhaps 100,000, or by some estimates, as far as 200,000 astronomical units. This is where the spherical symmetry is most complete. Objects here orbit with no preference for any particular plane. They hang in every direction, above the solar system, below it, perpendicular to it, isotropic, a word that means equal in all directions, and which does not quite carry the strangeness it deserves. The objects themselves are thought to be the frozen remnants of the early solar system. Not the large, differentiated bodies that became planets. Those stayed close in, grew large, sorted themselves by gravity and heat. What ended up in the Oort cloud are the smaller bodies. The planetesimals, chunks of ice and rock that formed in the region of the giant planets, were flung outward by gravitational interactions over hundreds of millions of years, and eventually settled into these remote, slow, nearly circular orbits far from everything they began near. They are, in a sense, the solar system's exiles, the material that did not get incorporated into anything larger, stored in the cold. The temperature at these distances is approximately 4 to 5 Kelvin, just a few degrees above absolute zero. This is colder than the coldest place naturally occurring on Earth by a margin that makes comparison feel almost comic. Absolute zero is the temperature at which all thermal motion ceases, the floor of cold that physics will not let anything reach. The Oort cloud objects sit just above that floor. They have sat there, essentially unchanged, for something close to 4 billion years. In that time, Earth has seen the rise and fall of every species that has ever lived on it. Oceans have formed and dried. Mountains have risen and eroded. And the objects in the Oort cloud have simply continued their slow orbits, frozen, silent, unchanged. There is something the mind reaches for when it tries to hold this image, a structure surrounding the sun on all sides, spherical, enormous, unlit, ancient, inferred but never seen. The nearest comparison that does any justice to it is this. Imagine that the solar system has an attic. Not a basement, not a garage, but an attic. A space above and around and beneath everything, where the building materials of the early solar system were stored when they were not needed. Where the leftovers went when the construction was finished. And that attic is so large that no one has ever been to it. No camera has ever pointed at it clearly enough to see inside, and the only evidence it exists at all is what occasionally falls out of it and drifts, glowing, past the inner planets, arriving as a comet, briefly brilliant before fading back into the dark. That is the Oort cloud, the attic of the solar system, the outermost room of the only home we have ever known. It is not visible from Earth. It is not visible to any telescope currently in operation. The individual objects within it are too small and too distant to resolve with current technology. Even if every telescope humanity has ever built were pointed at the same patch of Oort cloud sky simultaneously, they would see nothing. The objects are too cold to emit meaningful infrared radiation, too dark to reflect significant sunlight at that distance, too small and too spread out to coalesce into anything detectable. What we know about it comes from the comets it sends us, and from the physics that demands it be there, and from calculations that have grown steadily more sophisticated since Oort first sketched the idea in 1950, in a paper that proposed the existence of one of the largest structures in the solar system from the behavior of a few dozen comets. The understanding has a kind of elegance that science occasionally produces, a vast conclusion derived from modest evidence, the way a skilled reader can infer an entire library from a handful of borrowed books. We know the cloud is there. We know roughly where it begins and roughly where it ends. We know something of what it contains and something of how it came to be. What we do not yet have, what may take generations of better instruments to achieve, is any direct image of it. Any confirmed photograph of a specific Oort cloud object in its natural orbit. It remains, for now, the largest structure in the solar system and the least seen. And that gap, between the certainty of its existence and the complete absence of any direct observation, is itself a kind of measure of its scale. We cannot see it not because our instruments are primitive, but because the distances involved make even our best instruments small. That distance is where we are going next. because knowing the Oort Cloud exists and knowing how far away it actually is are two experiences that do not resemble each other. The name and the concept can be held in the mind without difficulty. The numbers are something else entirely. There is a particular kind of failure that happens when the human mind encounters very large numbers. It is not confusion exactly. The number is understood. It can be read aloud, written down, entered into a calculator. The arithmetic works. But something else fails: the felt sense of what the number means, the inner experience of its size. And in astronomy, this failure happens regularly, quietly, and the only solution anyone has found is to stop presenting the number alone and start building a bridge between it and something the body already understands. So let us build that bridge carefully. Let us begin with the unit. 1 astronomical unit. 1 AU. This is the average distance between the Earth and the Sun, approximately 93 million miles, or about 150 million kilometers. Light, traveling at 186,000 miles per second, covers that distance in about 8 minutes and 20 seconds. When you look at the Sun, you are seeing it as it was 8 minutes ago. The light entering your eyes left the Sun before you poured your morning coffee. That is 1 astronomical unit. Hold it. Neptune, the outermost of the 8 planets, orbits at approximately 30 astronomical units from the Sun, 30 times the Earth-Sun distance. Light from the Sun takes roughly 4 hours to reach Neptune. If you sent a radio signal to a spacecraft near Neptune, you would wait 4 hours for it to arrive, and 4 hours more for the reply. Voyager 2, which flew past Neptune in 1989, took 12 years to get there after launch. 30 astronomical units feels remote. It is remote, and it is, in the context of what we're about to discuss, essentially the front porch. The Kuiper Belt, the broad disk of frozen objects where Pluto lives, where hundreds of thousands of icy bodies orbit in the plane of the solar system, extends from about 30 astronomical units out to roughly 50. 50 AU. Light takes just under 7 hours to travel that far. Voyager 1, which did not visit Neptune but took a different trajectory, was beyond 50 astronomical units by the late 1980s. The heliopause, the boundary of the solar wind, the threshold Voyager 1 crossed in 2013, sits at approximately 120 astronomical units, 120 times the distance from Earth to the Sun. The Sun, from that distance, has dimmed considerably, though it remains the brightest object in the sky. Voyager 1 is currently around 160 astronomical units from the Sun. It has been traveling for nearly 5 decades. It is the most distant human-made object in existence. The inner edge of the Oort Cloud begins at approximately 2,000 astronomical units. Let that settle for a moment. Voyager 1, after nearly 50 years of uninterrupted travel, covering roughly 38,000 miles every hour, has reached 160 astronomical units. The inner boundary of the Oort Cloud sits at 2,000. By that measure, Voyager has covered less than 1/10 of the distance required to reach even the beginning of the structure we are discussing. At its current speed, it will take approximately 300 years to reach the inner edge of the Oort Cloud. 3 centuries from now. To put that in human terms, 300 years ago, the steam engine had not yet been invented. The United States did not exist. Isaac Newton had recently published his laws of motion and was still alive. The fastest machines humanity has ever built have not, in all the decades since the space age began, traveled far enough to reach the beginning of the outermost layer of our own solar system. That is the inner edge. The outer edge is something else entirely. Estimates for where the Oort Cloud ends, where the Sun's gravity finally loses its hold over orbiting objects, range from 50,000 to 200,000 astronomical units. The precise boundary depends on which gravitational model you use, how you account for the galactic tide, and what criteria you apply for what counts as being gravitationally bound to the Sun. But even the conservative estimate, 50,000 astronomical units, represents a scale that makes every familiar measurement feel like a toy. At Voyager's current speed, reaching the outer edge of the Oort Cloud, the far wall of the solar system, would take somewhere between 14,000 and 28,000 years. For context, 14,000 years ago, the last ice age was ending. Human beings had not yet developed agriculture. The oldest known cave paintings were being made. Everything that has happened since, every civilization, every war, every invention, every generation of every family that has ever lived, fits inside the travel time required to cross the Oort Cloud in our fastest spacecraft. The numbers begin to resist domestication at this scale, but let us try one more. 1 light year is the distance light travels in a single year, approximately 5.88 trillion miles, or 63,241 astronomical units. At this unit, the Oort Cloud finally becomes describable in compact terms. Its outer boundary, at 100,000 to 200,000 astronomical units, translates to approximately 1.6 to 3.2 light years from the Sun. And here is where the number produces its most striking effect. The nearest star to our Sun is Proxima Centauri, a small red dwarf located approximately 4.24 light years away. The next nearest, Alpha Centauri A and B, orbit each other at a distance of 4.37 light years from us. These are our closest stellar neighbors, the stars most frequently mentioned when people discuss interstellar travel, the targets most often proposed for any hypothetical future mission beyond the solar system. Proxima Centauri is 4.24 light years away. The outer edge of our Oort cloud may extend 1.6 to 3.2 light years from the Sun. This means the Oort cloud does not end somewhere safely inside the solar system, with a clean gap of empty interstellar space before the next star begins. It extends, by the best current estimates, somewhere between 1/3 and 3/4 of the way to the nearest star. Not to the midpoint, not to some abstract interstellar boundary, nearly to our neighbor. What this means in practice is that the solar system is not a small contained structure orbiting inside a vast ocean of interstellar space. It is a large, diffuse, poorly bounded structure whose outermost regions blend at the edges toward the space between stars. The edge of the solar system and the beginning of interstellar space are not two distinct places separated by a clear line. They are a gradation, a slow fading of one thing into another, across distances measured in light years, across timescales measured in millions of years. And we have not visited any of it. Consider Voyager 1 again. The probe is often described as humanity's most distant emissary, the object that has traveled farther from Earth than any other. And it has. At 160 astronomical units, it is an extraordinary achievement of engineering, navigation, and longevity. It is still transmitting. It is still sending back data from a distance so vast that even its radio signals traveling at the speed of light take more than 22 hours to reach Earth. But in terms of the solar system's actual extent, Voyager 1 has barely moved. It has covered less than 0.1% of the distance to the outer Oort cloud. If you scale the entire solar system from the Sun to the outer edge of the Oort cloud down to the length of a football field, Voyager 1 would currently sit less than 4 inches from one end zone. The other end zone, representing the far wall of the cloud, would be 100 yards away. The inner edge of the Oort cloud would be around the 10-yard line. We are still in the grass behind the goalpost. There is a temptation, when confronted with numbers like these, to obstruct them. to let them pass through the mind as impressive but ultimately meaningless figures, the kind of astronomical quantities that are understood to be large without being felt as large. But it is worth resisting that temptation here, even briefly, and allowing the numbers to do what they are actually trying to do. They are trying to tell you that the solar system is not small, that the diagram you were shown, the one with the sun at the center and the planets arranged outward and a clean edge somewhere near Neptune, was a convenience, not a portrait. That the real solar system is a structure so large that no human being has traveled beyond its innermost regions, and no machine we have ever built has come close to crossing it. That when you look at the night sky and see the stars, those stars are separated from us not by empty space that begins at the heliopause, but by space that begins only after passing through a vast and ancient cloud of frozen objects whose outer edge nearly reaches another star. The scale is hard to believe. That is the title, and it is not an exaggeration. The scale is genuinely hard to believe, not because the numbers are poorly understood, but because the numbers describe something for which the human nervous system has no reference. No landscape, no ocean, no experience of travel on Earth or in orbit prepares the mind for distances measured in tens of thousands of astronomical units. The mind reaches for the number and finds it, and the feeling of size still does not come. What comes instead is something quieter, a kind of stillness. The recognition that the solar system, the structure we were born inside and have never left, is so large that we have never seen its edges, never visited its outermost rooms, and may never send anything there in any human lifetime now foreseeable. And yet those rooms exist. They are out there now, as you listen to this, in the dark and the cold beyond any probe, any signal, any human trace. Orbiting in slow silence, part of the same solar system as the warm planet beneath you. That distance between here and there, between the known and the merely inferred, is what we are going to sit with for the rest of this video. Beginning with what it actually feels like, from the surface of a world out there, to look back and try to find the sun. Imagine for a moment that you are standing on a surface. Not Earth's surface, you're too far for that. You're standing on the surface of a small, frozen object somewhere in the outer Oort Cloud, perhaps 100,000 astronomical units from the sun. The ground beneath you is ice and dark rock. The temperature around you is approximately 4 Kelvin, colder than anything in ordinary human experience, colder than the surface of Pluto, colder than the coldest point ever recorded in a laboratory on Earth. Your breath, if you could breathe, would freeze before it left your lips. You look up. The sky above you is extraordinary. With no atmosphere to scatter light, every star in the Milky Way hangs visible and still. Hundreds of billions of them, in a band across the darkness more vivid and dense than any human eye has ever seen from Earth's surface. It is, in the most literal sense, a clearer view of the galaxy than any human being has ever had. And somewhere in that sky, among those hundreds of billions of stars, is the sun. You look for it, and you find it, because the sun, even at 100,000 astronomical units, is still the brightest star in your sky. It is still more luminous than Sirius, more luminous than Alpha Centauri. It is visible. But it is not recognizable. It is a point of light. A bright point, brighter than the other stars, but by a margin that diminishes with every unit of distance you add. There is no disk. There is no warmth you can detect at this distance. There is no sense of the sun as the enormous radiating presence it is from Earth. There is only a bright dot, hanging in the dark among hundreds of billions of other dots, distinguished by its brightness alone. To put this in measurable terms, the apparent brightness of the sun, as seen from Earth, has a magnitude of about -27. This is an astronomical measurement. The more negative the number, the brighter the object appears. From the outer Oort cloud, at 100,000 astronomical units, that magnitude drops to somewhere around -6.5 to -7. For comparison, Venus at its brightest appears at roughly -4.9 when seen from Earth. The full moon sits at -13. So the sun, from the outer Oort cloud, appears not much brighter than Venus does from Earth on a clear evening. Distinct, visible, but not overwhelming. Not a sun, a star. Light from the sun takes 8 minutes to reach Earth. At 100,000 astronomical units, given that 1 light year equals approximately 63,241 astronomical units, the travel time becomes roughly 1.58 years. The light you would see standing out there left the sun a year and a half ago. An event that happened on the sun this morning would not be visible from the outer Oort cloud for another 18 months. The sun you see is already history. The warmth is something else entirely. At Earth's distance, the sun delivers roughly 1,361 watts of energy per square meter. Enough to warm the planet, drive the weather, power the photosynthesis that underlies almost all life on Earth's surface. At 100,000 astronomical units, the energy delivered by the sun is so small it is difficult to express in useful terms. It is not merely cold, it is the functional equivalent of no warmth at all. An object at that distance receives heat from the sun at a rate so infinitesimal that the ambient temperature of the universe, the cosmic background radiation left over from the Big Bang, sitting at approximately 2.7 Kelvin, contributes more energy than the sun does. Think about what that means for a moment. The leftover warmth of the Big Bang, distributed across the entire observable universe, is a more significant heat source at that distance than the star those objects technically orbit. In simple terms, the sun does not heat the Oort cloud. The Oort cloud is not warmed by its star. It sits in a thermal environment that is essentially equivalent to the middle of intergalactic space. The connection between these objects and the sun is gravitational, not thermal, not optical. The sun does not illuminate them in any meaningful sense, does not warm them, does not reach them with its wind. Its only claim on these objects is the faint, patient pull of gravity. A pull so weak across that distance that an object in the outer cloud takes somewhere between 1 million and 30 million years to complete a single orbit. One orbit, 1 year out there, lasts longer than the entirety of human evolution. And yet, these objects orbit, they circle. They belong, in the technical gravitational sense, to the solar system, to our sun, to the same star that rises every morning over every city and ocean and forest on Earth. The same star that warms skin and drives seasons and makes the corn grow and lights the face of the moon. That star, from the outer Oort cloud, is a cold point of light among hundreds of billions of cold points of light, distinguishable by its brightness alone. But its gravity is still there. stretched thin across a distance almost too large to describe, but present. There is something in this that resists ordinary language. The objects in the outer Oort cloud belong to the sun the way something might belong to a place it can barely remember. Gravitationally attached, yes. Technically, members of the solar system, yes. But warmed by it? Lit by it? Touched by it in any way that would register as presence? No, not really. Not in any sense that matters to the ice and rock sitting out there in the 4 Kelvin dark. For context, consider the journey that light makes. 8 minutes from the sun to Earth. 4 hours from the sun to Neptune. 22 hours from the sun to Voyager 1's current position. And from the sun to the outer Oort cloud, 1.5 years. A year and a half of uninterrupted travel at the fastest speed the universe permits to cross the distance from the center of our solar system to its outermost edge. Voyager 1 broadcasts back to Earth at a power of roughly 22 watts, about the same as a standard compact fluorescent light bulb. That signal, spreading outward in a sphere as it travels, is so faint by the time it reaches Earth that the receiving antennas of the Deep Space Network have to work at the very edge of detection to hear it. And Voyager is only 160 astronomical units away. In the outer Oort cloud, at 100,000 AU, that same signal would have spread across a sphere more than 600 times wider in radius. Its power at the receiving end would be unmeasurably small, effectively zero. No communication technology we currently possess could maintain contact with a probe in the outer Oort cloud. Not because of a technical limitation we might overcome with better engineering, though that is also true, but because the distances involved impose fundamental physical constraints on how much signal survives the journey. The outer Oort cloud is not merely far. It is communicatively isolated from Earth in a way that our current civilization has no practical means of bridging. And even if we could send a signal there, it would take 1.5 years to arrive. Any response would take another 1.5 years to return. A simple exchange, a question and its answer, would take 3 years minimum. Any mission to the outer Oort cloud would not be a mission in the sense we use the word for Mars rovers or Saturn orbiters, where scientists on the ground can monitor, adjust, redirect, and respond in something like real time. It would be something categorically different. A release, a sending out, a trust that whatever was launched would still function after a journey lasting centuries, arriving at a destination that would look, from the spacecraft's perspective, like a dark and featureless sky with a single bright star at its center. That star, faint and distant, is home. This is what the scale of the Oort cloud actually means in human terms. Not just that it is far, everything in astronomy is far, but that it is so far that the sun itself becomes just another star when viewed from there. That the thermal and optical influence of our sun, which defines every aspect of life and weather and season on Earth, extends to the inner Oort cloud and then fades, and by the outer cloud has dwindled to something a thermometer would struggle to register. That the objects out there orbit our star without being lit by it, without being warmed by it, in a silence and a cold that has persisted unchanged since the early solar system. They were thrown out there billions of years ago by the violence of a young solar system still sorting itself out, and they have remained ever since in the dark, orbiting a sun that is to them only a distant star, part of a system they can barely feel the pull of. And what sent them there, what the mechanism was, what catastrophe arranged these objects into this vast and frozen shell, is a story that begins with the solar system's earliest and most disorderly period. A time when the giant planets were young and restless, and the inner solar system was a very different place from the one that eventually gave rise to Earth. The solar system, in its earliest period, was not the orderly arrangement of objects that the diagrams suggest. It was not 8 planets in stable orbits, each minding its lane, each settled into the path it would follow for billions of years. It was a disk of gas and dust and ice and rock in constant motion, objects colliding and merging and shattering and being flung outward by gravitational interactions so violent and so frequent that the solar system we have now, calm, structured, predictable, is almost unrecognizable as the descendant of what existed 4.5 billion years ago. Understanding the Oort Cloud requires going back to that period, because the Oort Cloud is not a structure the solar system built deliberately. It is a structure the solar system built by accident. It is the residue of a catastrophic early history, frozen in place at a distance so great that almost nothing has disturbed it since. In the first few 100 million years after the Sun formed, the region that now contains the giant planets, Jupiter, Saturn, Uranus, Neptune, was crowded with material. Planetesimals by the billions, bodies ranging from a few kilometers to hundreds of kilometers across, drifted through the disk in orbits that were unstable by modern standards. Collisions were common. Mergers built larger and larger objects. But not all of the material was incorporated into the growing planets. A great deal of it was in the wrong place at the wrong time, orbiting at the wrong distance, with the wrong velocity. And the giant planets, as they grew, were not passive presences. Jupiter, the largest planet in the solar system, has a mass more than twice that of all the other planets combined. Its gravitational influence on nearby objects is profound. Saturn, though smaller, adds its own considerable pull. As these two planets grew and settled into their early orbits, they began flinging smaller bodies outward, not gently, not gradually, but through close gravitational encounters that could change an object's orbit dramatically in a single pass. A planetesimal that wandered too close to Jupiter could be hurled outward at velocities that carried it far beyond the forming solar system's familiar disk. Some of these objects were ejected entirely, flung into interstellar space on hyperbolic trajectories, never to return. These are lost to the solar system forever. But many others were sent into highly elliptical orbits, elongated loops that carried them far out into the distant solar system, and then, after millions of years, brought them back in again. The initial energy of the Jupiter encounter would have sent them outward, but other forces were at work on their return. This is where the galactic tide enters the picture. The Milky Way is a galaxy of hundreds of billions of stars, arranged in a spiral disk roughly 100,000 light-years across. Our Sun sits in one of the outer spiral arms, orbiting the galactic center along with everything in the solar system. And as the solar system moves through the galaxy, it experiences a tidal force, the same kind of gravitational gradient that causes Earth's oceans to bulge toward and away from the Moon, but operating at a scale that defies easy comparison. The galactic tide is subtle. On any individual orbit of a nearby solar system object, it has a negligible effect. But on an object in a wide, long-period orbit, a planetesimal that Jupiter has flung into an ellipse taking millions of years to complete, the galactic tide acts over timescales long enough to accumulate. Over many orbits, the galactic tide gradually reshapes these elongated trajectories. It rounds them out. It lifts the perihelia, the closest approach points to the Sun, so that these objects no longer swing back through the inner solar system on each orbit. Instead, they settle into more distant, more circular orbits. Orbits that keep them perpetually in the outer dark, never again approaching the Sun closely enough to be scattered further. This is the mechanism. Jupiter flings objects outward. The galactic tide, over millions of years, rounds and lifts their orbits. The objects settle into the vast, slowly orbiting sphere that Oort identified from the behavior of the comets that occasionally fall back inward. The process that created the Oort Cloud was not a single event. It unfolded over hundreds of millions of years, during and after the period of heavy bombardment while the solar system was still young and chaotic. The NICE model, a leading theoretical framework for the early solar system's dynamics, developed in the early 2000s by a team of astronomers working in Nice, France, describes a particularly dramatic version of this history. In the NICE model, the giant planets did not form in their current positions. They formed closer together, in more compact orbits, and then migrated, Jupiter moving slightly inward, Saturn, Uranus, and Neptune moving outward, crossing orbital resonances in the process that triggered a period of intense disruption. In this period, billions of planetesimals were scattered throughout the solar system. The inner solar system experienced a rain of impactors, the period called the Late Heavy Bombardment, preserved in the cratered faces of the Moon and Mars and Mercury. And the outer solar system experienced a clearing. The giant planets, migrating and interacting, ejected the vast majority of the planetesimals that had existed in their neighborhood. Some went to the Kuiper Belt. Many more went to the Oort Cloud. The rest were ejected into interstellar space entirely. The Oort Cloud, in this picture, is the record of that upheaval. It is the surviving remnant of the billions of bodies that Jupiter and Saturn and the other giants could not hold close, could not incorporate, and could not entirely release. Objects that were flung far enough to survive, but not far enough to escape. The in-between population. The exiles that could not quite leave. There is a kind of geological analogy for what the Oort Cloud represents. When geologists examine a rock formation, they are reading a record of past events, pressure, heat, the movement of ancient seas. The rock is the aftermath of history, frozen in physical form. The Oort Cloud is something similar. It is the frozen aftermath of the solar system's most violent period. Every object out there carries, in its orbit and its composition, the record of a close encounter with a giant planet billions of years ago. The gravitational fingerprint of Jupiter or Saturn, laid down in the early solar system and preserved, unchanged, in the cold of the outer dark. Passing stars contribute another layer to this history. Over the 4.5 billion year lifetime of the solar system, thousands of other stars have passed within a few light years of the Sun. None have come close enough to dramatically alter the planetary orbits. The planets are bound tightly enough that stellar flybys at these distances produce only minor effects. But on the outer Oort Cloud, where objects are only loosely tethered, a passing star can produce significant perturbations. It can nudge the orbits of outer cloud objects inward, sending some of them on long, slow falls toward the inner solar system. It can also strip some objects from the cloud entirely, carrying them off as the star moves on. The cloud we have now is the product of all of this, of Jupiter's flinging and Saturn's nudging, of the galactic tide's patient reshaping, of billions of years of stellar flybys gently disturbing the outermost orbits. The cloud that Oort inferred from 1950s comet data is not the same cloud that formed in the solar system's early period. It has been modified by 4 billion years of subtle forces, slowly stirred by the galaxy it moves through, occasionally losing objects to the interstellar medium, and occasionally receiving perturbing nudges that send others falling inward. It is, in a sense, a living structure, not alive in any biological meaning, but dynamic over geological and astronomical timescales, not static, not finished, still being shaped, slowly, by forces that operate over millions of years. And the evidence for all of this? The comets. The long-period comets that arrive in the inner solar system from every direction with no preference for any particular angle, exactly as Oort predicted. Each one is a fragment of this history, a piece of material that was formed in the early solar system, thrown outward by a giant planet, carried to a distant orbit by the galactic tide, and then nudged inward again millions or billions of years later by a passing star, or a gravitational resonance, or some other perturbation too subtle to easily identify. Each long-period comet is, in this sense, an artifact, a messenger from the solar system's most violent early period, returning after an absence measured in geological epochs. What those messengers tell us, and what they look like when they finally arrive after millions of years in the cold and the dark, is where we are going next. Because the comets are not abstract. They are visible. They have been watched by human eyes for all of recorded history. And what they carry with them, from the edge of everything, is something the Oort Cloud can offer in no other way. For as long as human beings have looked at the night sky, comets have interrupted the stillness. They appear without warning, or what felt like without warning, in the centuries before orbital mechanics made prediction possible, drifting slowly across the starfield over days and weeks, trailing a luminous tail that could stretch across a significant portion of the visible sky. They were unlike anything else in the heavens. The stars did not move, or move so slowly the motion was imperceptible in a human lifetime. The planets wandered, but in regular and eventually predictable paths. Comets were different. They arrived. They were present for a time, and then they were gone. Every ancient civilization that left written records also left records of comets. Babylonian astronomers cataloged them. Chinese imperial historians recorded them in careful detail. Dates, durations, directions of travel, lengths of tails, going back more than 2,000 years. Greek philosophers debated their nature. Were they atmospheric phenomena, disturbances in the upper air, or something genuinely celestial? Roman writers treated them as omens, harbingers of the deaths of emperors, the falls of kingdoms, the arrivals of catastrophe. In the Bayeux Tapestry, embroidered to commemorate the Norman conquest of England in 1066, Halley's Comet appears in the upper border, and below it, a row of figures stares upward in visible alarm. The fear was understandable. In a sky that was otherwise constant, a comet was change. And change, in the ancient imagination, meant consequence. We understand now what a comet actually is. A comet is a small body, typically a few kilometers to a few tens of kilometers across, composed of ice, dust, rock, and organic compounds. For most of its existence, it is invisible. A dark, irregularly shaped object tumbling slowly through space, too cold and too distant to emit any detectable light, too small for any telescope to resolve at interstellar distances. It exists in the outer solar system as an anonymous member of a vast population. Nothing about it, for most of its history, distinguishes it from the billions of similar objects surrounding it. Then it falls inward. Something disturbs its orbit. Perhaps a passing star nudges it very slightly, imperceptibly altering the geometry of its path. Perhaps the galactic tide has accumulated enough influence over millions of years to shift its trajectory. Whatever the cause, the perturbation is enough. The object, which has orbited in the cold for perhaps 1 billion years, begins a long, slow fall toward the inner solar system. That fall, from the outer Oort Cloud, takes millions of years. The object accelerates gradually as the sun's gravity grows stronger. It crosses the orbit of Neptune, the orbit of Uranus, the asteroid belt. It warms, slightly, then more, then dramatically as it nears the sun. And then, inside roughly 3 astronomical units from the sun, inside the orbit of Mars, something visible happens. The sun's heat begins to sublimate the surface ices. Water ice, carbon monoxide ice, carbon dioxide ice. They do not melt, because in the vacuum of space there is no liquid phase to pass through. They go directly from solid to gas, carrying dust particles with them as they escape the comet's surface. This outgassing forms a coma, a diffuse atmosphere of gas and dust surrounding the comet's nucleus that can swell to a size larger than some planets. The solar wind then sweeps this material into a tail, 2 tails actually, a dust tail curving gently behind the comet along its path, and an ion tail pointing directly away from the sun, pushed by the solar wind regardless of the comet's direction of travel. And what was invisible for a billion years becomes, for a few weeks or months, one of the most spectacular objects in the night sky. This is what a comet is. Not a visitor from nearby. Not something that formed in the inner solar system and wandered outward. A genuine artifact from the distant reaches of the solar system. From the Oort Cloud itself in the case of long-period comets, making its first approach to the sun in an interval of time so long that the civilization watching it today is likely not the civilization that last saw it, if any civilization existed to see it then. Comet Hale-Bopp, which appeared in Earth's skies in 1996 and 1997, was one of the brightest and most studied comets of the 20th century. Its nucleus was estimated at roughly 60 kilometers across, unusually large for a comet, which is part of why it was so spectacular. Its orbital period, the time required for a complete loop around the sun, is approximately 2,520 years. The last time Comet Hale-Bopp passed through the inner solar system, around 500 BCE, the Roman Republic was in its early centuries. The Buddha had recently died, and the Parthenon had not yet been built. Before that visit, it had spent thousands of years in the outer solar system, cold and invisible, waiting. Comet West, which appeared in 1976, has an orbital period estimated in the hundreds of thousands of years. The last time it visited the inner solar system, modern humans had not yet migrated out of Africa. It arrived, blazed briefly in the dawn sky for a few weeks, and fell back outward into the dark, where it will remain, by all estimates, for longer than the entirety of recorded human history, before returning again, if it returns at all. McNaught's comet, which blazed across southern hemisphere skies in 2007, is thought to have a hyperbolic orbit, meaning it approached the sun from the outer Oort cloud and will not return. The gravitational interaction with the planets during its perihelion passage altered its orbit just enough to give it an escape trajectory. It is now leaving the solar system, heading into interstellar space, carrying material that formed with our sun 4.5 billion years ago. The felt quality of what a long-period comet represents is worth dwelling on. When you see a comet, whether through binoculars or a telescope, or even with the naked eye, you are observing an object that has spent most of its existence in absolute cold and darkness, beyond the reach of the sun's warmth, beyond the influence of anything except the faint tug of gravity and the slow whisper of the galactic tide. It has traveled, for this visit, a distance that no human machine has ever approached. It has arrived in the inner solar system for the first time in millions of years, or perhaps for the first time ever, and it announces its presence by briefly glowing, sublimating its ancient ices in the sun's heat, before falling back into the void. The light you see when you see a comet is the light of the outer solar system, briefly made visible. The outer solar system, which has no other way to show itself to us. And the Oort cloud's role in producing these objects is the primary reason we know as much about it as we do. Oort noticed that long-period comets arrive from all directions with equal probability, not preferentially from the plane of the solar system, not from one region of sky over another, but isotropically from a sphere, from every direction at once. The only structure that could produce this pattern is a spherical reservoir, a shell of objects surrounding the solar system on all sides, at great distance. Any other geometry would produce comets preferentially from certain directions, and the data did not support that. This is why the Oort cloud must be there. The comets say so. Each long-period comet is a data point confirming the spherical geometry of its origin. Each arrival from a different region of sky is another vote for the structure Oort proposed in 1950. And now, more than 70 years later, the inference has only grown stronger. More long-period comets have been cataloged. The isotropic distribution has held. The Oort cloud remains unobserved directly, but it has been confirmed indirectly over and over by the messengers it sends inward. And those messengers number, in terms of the full reservoir they represent, in the trillions. Which raises a question that deserves its own careful consideration. What does it actually mean to say that the Oort cloud contains 1 trillion objects? Not just numerically, but as a physical description of a structure. What does 1 trillion objects, spread across a shell of space, measured in tens of thousands of astronomical units, actually constitute? What is the Oort cloud as a population, as a collection of worlds? The estimate is not precise. It cannot be, given that no direct survey of the Oort cloud has ever been possible with current technology. But the best models, working backward from the observed population of long-period comets and forward from simulations of the early solar system's dynamics, converge on a number that sits between 100 billion and 2 trillion objects larger than approximately 1 kilometer in diameter. 1 trillion is the median of that range, and it is the number most often cited. 1 trillion objects. To develop any felt sense of what this means, it helps to place it next to something familiar. The Milky Way galaxy contains an estimated 200 to 400 billion stars. The Oort cloud, by the best current estimate, contains more individual objects than there are stars in our galaxy. More. And these are not particles, not grains of dust, not atmospheric molecules. These are solid bodies, chunks of ice and rock, each at least 1 kilometer across. Many are larger. Some, in the inner Oort cloud, may be hundreds of kilometers across. Not planets, but not negligible. Worlds, in the sense that they have surfaces, they have volume, they have gravity sufficient to pull themselves into roughly spherical shapes, if they are large enough. 1 trillion worlds. In the dark, in the cold, around one ordinary star. The mass of all this material is, by current estimates, only a few times the mass of Earth, perhaps 2 to 40 Earth masses in total, depending on the size distribution assumed for the objects. This seems paradoxical, 1 trillion objects adding up to only a few Earth masses. But it resolves when you consider how small most of the objects are and how vast the space they occupy. A kilometer-wide ball of ice and rock is genuinely small by planetary standards. 1 trillion of them, spread across a shell of space measuring hundreds of thousands of astronomical units in depth, produces a structure that is simultaneously enormous in extent and thin in density. The spacing is the key to this. If you distributed 1 trillion objects evenly across a spherical shell with an inner radius of 2,000 astronomical units and an outer radius of 100,000 astronomical units, the average distance between any two objects would be enormous. Not meters, not kilometers, astronomical units. Each object in the Oort cloud is alone in a meaningful sense, not surrounded by neighbors, not in a crowded disk like the asteroid belt or the Kuiper Belt, but separated from the nearest other object by distances that, on any human scale, would constitute vast emptiness. The Oort cloud is, paradoxically, both the most populated region of the outer solar system and one of the most sparsely inhabited. For context, consider the asteroid belt. The asteroid belt contains hundreds of thousands of objects larger than a kilometer, concentrated in a disk between roughly 2 and 3.5 astronomical units from the Sun. Spacecraft have passed through it multiple times: Voyager, Pioneer, New Horizons, Dawn, and none of them have ever come close to colliding with an asteroid. The belt is far emptier than science fiction has traditionally suggested. The objects are hundreds of thousands of kilometers apart on average. A camera pointed outward from within the belt would see empty space in every direction. Now extend that logic to the Oort cloud, where the volume is millions of times larger and the number of objects, though vast, is distributed across all of that volume. The average Oort cloud object orbits in isolation so complete that no other object of any significance exists within millions of kilometers of it. There is no light, there is no company, there is no reference point for size or direction or motion except the faint gravitational pull of the Sun, almost imperceptible at that distance, and the slow rotation of the galaxy above and below. What are these objects in physical terms? They are thought to be compositionally similar to comets, which makes sense, since long-period comets are Oort cloud objects that have been diverted inward. Their surfaces are likely very dark, covered in organic compounds and irradiation products, the result of billions of years of exposure to cosmic rays. Beneath the surface, they likely contain pristine ices, water ice, carbon monoxide, carbon dioxide, methane, ethane, and more complex organic molecules. The interiors of these objects are among the least processed material in the solar system. Protected from the sun's heat, protected from the solar wind, they may preserve the original chemical composition of the solar nebula from which the solar system formed, the raw material of planet formation, stored unchanged for 4.5 billion years. In this sense, the Oort cloud is not just large, it is old, in a way that most of the solar system is not. The inner solar system has been geologically active, plate tectonics on Earth, volcanism on Mars and Io, constant resurfacing by impact and erosion and chemical reaction. The Kuiper Belt has been stirred by the migration of Neptune. The asteroid belt has been depleted by billions of years of collisions. But the Oort cloud has been, since its formation, largely untouched. The objects out there are not just frozen in temperature, they are frozen in time. Chemically, compositionally, structurally, they are as close to the original material of the solar system as anything in existence. 4.5 billion-year-old ice, in the dark, beyond the reach of anything that might change it. When a long-period comet falls inward and begins to sublimate near the Sun, scientists who study the gases and dust it releases are, in a sense, reading that ancient record. The composition of a comet's coma is a chemical window into the early solar system. What molecules were present, what ratios, what structures. Every comet that visits the inner solar system delivers a small piece of that archive. But for every comet that falls inward and is observed, trillions remain in the outer dark, their archive intact and unread. We will not observe them. We do not have the instruments to detect them at that distance, and we do not have the technology to send anything to them. They orbit on, unnamed, uncatalogued, each one a separate world in complete isolation, each one carrying in its frozen interior a chemical record of the solar system's origin that no one will ever directly examine. There is a specific weight to this when you allow yourself to sit with it. A trillion objects, a trillion separate surfaces, each one cold and dark, each one orbiting in silence, at a distance our fastest probe cannot reach in any foreseeable human future. Some of them are large enough to have surface gravity. Some of them may have irregular, tumbling shapes, lobed or elongated, slowly rotating through the dark, with no sun to cast shadows on their surfaces and no observer to see them even if there were. They have been doing this, orbiting, tumbling, existing in the cold, since before Earth had an ocean, since before the moon formed from the debris of a giant impact, since before any life of any kind existed anywhere in the solar system. And they will still be doing it long after the sun has left the main sequence and expanded into a red giant. Long after the inner solar system has been sterilized by the sun's expansion, long after Earth itself has been engulfed or stripped bare, the outer Oort cloud will persist. The sun's eventual fate, the red giant phase, the planetary nebula, the cooling white dwarf, will alter the gravitational landscape slightly, and some outer cloud objects will drift away. But many, perhaps most, will remain, orbiting a dim white dwarf, still cold, still dark, still carrying their 4 billion-year-old ice. This is what the Oort cloud is, as a collection of worlds. Not one world, not a handful, not a number that the mind absorbs easily. A trillion separate objects, each alone, each unchanged, each part of a structure so large and so sparsely populated that even the idea of exploring it, of visiting even a tiny fraction of it, requires timescales that overlap with the lifetime of the sun itself. But holding all of this, the trillion objects, the vast distances, the cold and the silence, there is a question that has been quietly waiting. All of these objects orbit. They are bound to the sun, but the force binding them is so attenuated at these distances that calling it a firm grip would be generous. The sun's hold on the outer Oort cloud is, by any reasonable measure, tenuous. And understanding exactly how tenuous and what threatens to undo it takes us into one of the stranger corners of solar system dynamics. Gravity is the most patient force in the universe. It does not announce itself. It does not push or pull in any way that can be felt at ordinary human scales across cosmic distances. It simply exists, a curvature in space-time produced by mass, reaching outward in every direction, diminishing with distance according to a precise mathematical relationship. And that relationship, the inverse square law, is what makes the Oort cloud possible, and also what makes it precarious. The inverse square law states that gravity decreases with the square of the distance. Double the distance from a gravitational source, and the force drops to 1/4. Triple it, and the force drops to 1/9. The relationship is clean and unforgiving, and it means that at very large distances, even a very massive object exerts almost no gravitational influence at all. The Sun has a mass approximately 333,000 times that of Earth. At Earth's distance, 1 astronomical unit, this mass produces the gravitational force that holds us in a stable orbit, drives the seasons, and keeps the moon circling us with predictable regularity. It is, by the standards of human experience, an overwhelming force. At 100,000 astronomical units, the outer edge of the Oort cloud, that same sun's gravity has been weakened by a factor of 10 billion squared relative to its strength at 1 astronomical unit. The number is so large that it requires a moment's patience. 10 billion times 10 billion. 10 to the 20th power. The sun's gravitational pull on an outer Oort cloud object is 10 to the 20th power times weaker than its pull on the Earth. The force is not zero. It is real, measurable in principle, and sufficient to keep objects in orbit. But only barely, only very, very slowly. An object in the outer Oort cloud at 100,000 astronomical units, in a roughly circular orbit, moves at a speed of perhaps 100 meters per second. A fast sprinter runs at roughly 10 meters per second. An Oort cloud object at the outer edge of the solar system orbits the Sun at a speed approximately 10 times that of an Olympic sprinter. This is not impressive by astronomical standards. The Earth orbits the Sun at roughly 30 kilometers per second, 300 times faster. The orbital speed tells you how weakly the Sun is holding these objects. They drift, they creep. They take between 1 million and 30 million years to complete a single orbit. At this level of gravitational binding, other forces become competitive. Not dominant, the Sun's gravity, even this attenuated, is the primary force acting on most Oort cloud objects. But other gravitational influences, which are negligible in the inner solar system, become significant here. The most important of these is the galactic tide. The Milky Way is not a smooth, uniform gravitational field. As the solar system orbits the galactic center, it moves through regions of varying density, spiral arms with their concentration of stars and gas, the general disk with its own gravitational pull perpendicular to the orbital plane, the central bulge pulling from inside the orbit. All of this produces a tidal effect on the solar system as a whole. Just as the moon's gravity produces tides on Earth's oceans by pulling more strongly on the near side of Earth than the far side, the galactic gravitational field pulls more strongly on the near side of the solar system than the far side. This differential, the galactic tide, is too weak to affect anything in the inner solar system noticeably. But in the outer Oort cloud, where the Sun's own gravity is barely holding on, the galactic tide becomes a significant shaping force. Over millions of years, the galactic tide gradually shifts the orientations of Oort cloud orbits. It is this tidal force, acting over geological timescales, that is thought to be responsible for lifting the perihelia of some objects, raising the closest approach point of their orbits so they no longer swing through the inner solar system, and for lowering the perihelia of others, sending them on long, slow falls inward. Many long-period comets may owe their inward journeys not to a stellar flyby or a direct collision, but to the slow, patient accumulation of galactic tidal influence over millions of years. This means that the comets arriving in the inner solar system today are, in part, the product of forces operating on the scale of the Milky Way itself. The galactic tide, the gravitational influence of the entire galaxy, has been quietly reshaping the Oort cloud for billions of years, slowly stirring its outer layers, occasionally tipping an object inward toward the Sun. When you see a long-period comet in the night sky, you are, in a very real sense, seeing the galaxy's influence on the solar system made visible. Passing stars contribute a more episodic version of this disturbance. Over the solar system's 4.5 billion year history, many thousands of other stars have passed within a few light years. The closest known recent encounter was a star called Schultz's star, which passed within approximately 0.8 light years of the Sun, roughly 70,000 years ago. Close enough, some researchers suggest, to have perturbed the outer Oort cloud significantly, potentially triggering a modest increase in the rate of long-period comet arrivals that began sometime after the encounter. The delay between the stellar passage and the comet arrivals is expected because objects perturbed in the outer cloud take millions of years to fall inward. These encounters are not uniformly distributed in time. The solar system's orbit around the galactic center takes it through regions of varying stellar density, through spiral arms with higher concentrations of stars, and through the gaps between arms with fewer. This means the rate of stellar encounters, and therefore the rate of galactic tide perturbation, varies over hundreds of millions of years. Some researchers have proposed that periodic increases in the rate of long-period comet arrivals, and therefore periodic increases in the bombardment rate of the inner solar system, may be linked to the solar system's passage through the galactic spiral arms. There is another consideration, quieter and stranger. The outer Oort cloud sits near the outer boundary of the Sun's Hill sphere, the region within which the Sun's gravity dominates over the galactic gravitational field. Inside the Hill sphere, an object is bound to the Sun. Outside it, the galactic field wins, and the object drifts away permanently. The Hill sphere extends roughly 100,000 to 200,000 astronomical units from the Sun, the same range as the Oort cloud's outer boundary. This is not a coincidence. The Oort cloud's outer edge is, in a sense, defined by the Hill sphere. The cloud ends where the Sun's gravitational dominance ends. Objects near the outer boundary of the Oort cloud live in a gravitational margin. They are technically bound to the Sun, but only just. A small perturbation from a passing star, from the galactic tide, from a gravitational resonance, can be sufficient to push them over the edge into the galactic field. Some researchers believe that the Oort cloud loses objects continuously from its outer layers, a slow evaporation that has been ongoing for billions of years. The cloud we observe today, through its comet messengers, may be significantly depleted compared to the original population that formed in the solar system's early period. And this raises a thought that deserves a moment of stillness. The outer Oort cloud is not a possession. It is not a firmly bounded domain, a clear and settled territory belonging unambiguously to the Sun. It is a margin, a borderland, the place where belonging becomes uncertain, where the Sun's claim on matter becomes thin enough to be contested by the gravitational field of an entire galaxy. The objects out there do not know, in any meaningful sense, whether they belong to this star or to the galaxy that contains it. They orbit at the threshold. They exist in the narrow zone between solar system and interstellar space. And beyond that threshold, beyond the outer edge of the Hill sphere, beyond the last objects the Sun can hold, there is a region of space that connects the Oort cloud to the equivalent structures around neighboring stars. The gap between solar systems, which looks like an absolute boundary on any diagram, is in fact a gradation. A region where neither star fully dominates, where the interstellar medium fills the space between two diffuse, overlapping halos of frozen material. It is that gap and what it implies about the relationship between our solar system and those around us that takes us to the last piece of this picture. The distance between stars is the fundamental fact of interstellar space. It is the number that ends every conversation about interstellar travel, that grounds every meditation on cosmic isolation, that explains in the simplest possible terms why the universe, despite containing hundreds of billions of galaxies, each containing hundreds of billions of stars, feels so profoundly empty at the human scale. The nearest star is 4.24 light years away. That is 25 trillion miles. That is a distance so large that light, which crosses the Earth in a fraction of a second, which travels from the Moon to the Earth in just over a second, which covers the distance from the Sun to Earth in 8 minutes, takes more than 4 years to cross it. There is no shortcut. There is no tunnel, no fold, no currently known physical mechanism for crossing that gap in anything shorter than the time light itself requires. Our fastest probe, Voyager 1, moving at roughly 38,000 miles per hour, would take approximately 75,000 years to cover the distance to Proxima Centauri, if pointed in that direction, which it is not. The gap between our sun and the nearest star is, by any practical measure of human civilization, absolute. But it is not as featureless as it seems, and the Oort Cloud is part of the reason why. Consider the geometry. Our Oort Cloud, by best current estimates, extends to somewhere between 100,000 and 200,000 astronomical units from the Sun. In light-year terms, that is between 1.6 and 3.2 light-years. Proxima Centauri is 4.24 light-years away. If both our Sun and Proxima Centauri have their own equivalent outer halos, their own populations of loosely bound icy objects surrounding them in roughly spherical shells, then the outer edges of those two halos exist within a few light-years of each other. By the outer estimates, they could be less than a light-year apart. By some estimates, they might nearly touch. We do not know whether Proxima Centauri has its own Oort cloud. The dynamics that create such a structure depend on the presence of giant planets to fling material outward, and the galactic tide to reshape orbits, and a suitable population of early planetesimals to serve as raw material. Whether Proxima Centauri, a small red dwarf, the smallest and faintest of a triple star system, has the right conditions for an equivalent structure is not yet known. But the physical processes that produce Oort clouds are general, not specific to our solar system. Many stars, perhaps most, may have analogous reservoirs of loosely bound material at their outer margins. If so, the space between stars is not the absolute void it appears to be on any diagram. It is populated, sparsely but genuinely, by the outermost material of the stars on either side. The gap between solar systems, measured from Oort cloud edge to Oort cloud edge, is smaller than the gap measured from planet to planet. The interstellar medium, the thin gas and ancient radiation filling the space between stars, is not perfectly empty even now. It contains hydrogen atoms at densities of roughly 1 per cubic centimeter, interstellar dust, cosmic rays, magnetic fields. And it may, in the zone between two nearby stars, contain the outermost and most loosely bound members of two separate stellar families, drifting in orbits so wide and so slow that they represent the most ghostly possible form of belonging. There is observational evidence that the boundary between solar systems is not impermeable. In 2017, astronomers detected an object passing through the inner solar system on a trajectory that was definitively hyperbolic, meaning it was not bound to the Sun and had originated from elsewhere. They named it Oumuamua, from a Hawaiian word meaning something like a messenger from far, arriving first. It was elongated, tumbling, dark, and unlike any solar system object previously observed. It accelerated slightly as it left the solar system, in a way that simple gravity alone could not fully explain, a mystery that has since been the subject of considerable scientific attention. In 2019, a second interstellar object was detected, Comet Borisov. This one was unambiguously a comet. It displayed a coma, it outgassed, it behaved in every measurable way like a long-period comet from the outer solar system, except that its trajectory was clearly hyperbolic, its origin clearly interstellar. Borisov came from somewhere else, another star, another solar system. It passed through ours, swung around the Sun, and continued outward, a visitor that spent perhaps a few months in the inner solar system after a journey of unknown duration through interstellar space. These objects, Oumuamua and Borisov, are the first confirmed interstellar objects ever detected passing through the solar system. They will not be the last. Their detection implies that interstellar space is populated with objects that have escaped their home solar systems, drifting through the galaxy in the slowly expanding populations of ejected material. Some of what was flung out of our own solar system by Jupiter and Saturn billions of years ago did not make it to the Oort Cloud. It was ejected entirely into interstellar space. That material is out there now, somewhere, drifting, and equally, material from other solar systems, other early planetary systems, other giant planet flinging events, occasionally drifts through ours. The space between stars is not sealed. It is permeable, slowly, over geological timescales, to the loosest bound material of neighboring systems. Objects pass. Material exchanges. The interstellar medium carries, diluted almost beyond detection, the building blocks of solar systems that formed billions of years ago around stars that may no longer exist. This picture of overlapping halos, of permeable stellar boundaries, of slow material exchange across the gaps between stars, changes the shape of what the solar system is. It is not a closed system. It is not a bounded sphere with a clear inside and a clear outside. It is a concentration, a region where the sun's gravity dominates clearly, surrounded by a transitional zone where that dominance fades, bordered at its outermost edge by a margin where solar system and interstellar space blur together over distances measured in light years. The edge of the solar system is not a wall. It is a gradient, a slow change from densely bound inner system to the loosely tethered outer cloud, to the even more loosely associated fringe material, to the interstellar medium proper. There is no moment, no crossing point, no boundary equivalent to the heliopause in gravitational terms. There is only a gradual attenuation of the sun's claim on matter, until the claim becomes indistinguishable from the background. And sitting inside that gradient, somewhere between here and Proxima Centauri, are a trillion objects in the cold, orbiting slowly, unchanged since the solar system formed. Part of a structure so large that our fastest spacecraft has not yet reached its inner boundary, and will not in any human lifetime that can currently be foreseen. This is the hidden scale of the Oort Cloud. Not just that it is large in some impressive astronomical sense, but that it is large enough to reframe the solar system entirely. Large enough to close most of the gap between us and the nearest star. Large enough to make the concept of a solar system edge genuinely uncertain. Large enough to hold, in its cold and dark interior, a trillion worlds that no human being has ever seen, and no probe has ever visited, and no photograph has ever captured. It exists because of ancient catastrophe. It persists because of ancient cold. It reveals itself only through the comets it occasionally releases, sending them on long, slow journeys to the inner solar system where they glow briefly and then fall back into the dark. It is the largest component of the solar system, the oldest, the most distant, the least seen, and it surrounds everything: the sun, the planets, the earth, you, right now, in every direction, in the silent and invisible dark beyond everything the diagrams ever showed. There are things true about the place you live that are too large to be perceived. The Oort Cloud is one of them. And at a certain point, the honest response to a truth that large is not more data. It is something quieter, something more like sitting with it in the dark and letting the numbers dissolve back into the feeling they were always trying to produce. You have been listening for a long time now, longer perhaps than you intended. The numbers have come and gone, the astronomical units, the light years, the trillion objects, the 4 billion year ice. They have done what they were asked to do. They have built the structure and the imagination, laid out the distances, populated the dark with something real and vast and true. And now, at this point in the journey, the numbers can rest. What remains is the thing the numbers were always pointing toward. Not a fact exactly, more like a feeling that the facts, arranged carefully enough, eventually produce. A feeling of scale that is not frightening in the ordinary sense, not the sharp fear of a sudden danger, not the anxiety of something threatening and immediate, but the quieter kind of overwhelm that comes from understanding that you exist inside something whose edges you cannot see, cannot reach, cannot even meaningfully imagine. The Oort Cloud is there right now, not in some distant part of the universe, not around some other star, not in the deep past or the theoretical future. It is there now, surrounding you, surrounding this planet, this city, this room, this moment. A shell of frozen objects, a trillion of them by best estimate, orbiting in every direction above and below and beside the plane of the solar system, at distances ranging from thousands to hundreds of thousands of astronomical units. Every atom in your body is, at this moment, gravitationally bound to a structure that extends nearly 2 light years in every direction. You cannot feel this. The gravity of the Oort cloud is immeasurably too faint to register in any human sense. No instrument on the surface of the Earth can detect the individual objects out there. No telescope can see them. No signal has ever been sent to them, and yet they are real, inferred from the mathematics of comet orbits, confirmed by the physics of gravitational dynamics, accepted by the scientific community with as much confidence as is accorded to objects we have photographed in detail. There is a particular quality to things that are known but not seen. Mathematics describes them. Models predict their behavior. Observations confirm their existence indirectly through the traces they leave in the things that fall inward from them. But the direct experience of them, the image, the photograph, the visual confirmation that the human nervous system trusts most readily, is absent. The Oort cloud is known in the way a sound heard through walls is known. You did not imagine it. It is real. But you have never seen its face. This is not a failure of science. Science has done everything it can with the tools available, and the tools available are genuinely formidable. It is simply a measure of distance. The outer Oort cloud sits so far away that the light leaving it, the small amount of sunlight it might reflect at those distances, arrives at Earth so attenuated as to be unmeasurable against the noise of the cosmos. The objects are there, cold and dark and real, but they do not announce themselves. They have not announced themselves in all the history of human astronomy. They have been known only by inference for over 70 years, and they may remain known only by inference for generations more. This is one of the stranger aspects of the solar system when you stay with it long enough. The largest structure we are part of is the one we have never seen. The most distant members of our solar family are the ones we know least about. The place is enormous, and we occupy only the innermost fraction of it. We have sent machines to the planets, landed on some of them, driven across the surface of one, collected rocks from another. We have flown past the gas giants, photographed their storms and their moons in extraordinary detail, mapped the Kuiper Belt with increasingly capable telescopes. And all of that, the entirety of human exploration of the solar system, amounts to an examination of the innermost fraction of a percent of its total extent. The outer layers remain. The Oort cloud remains, not waiting for us in any purposeful sense, but simply persisting, as it has persisted for 4 billion years, in the cold and the silence beyond everything we have built, or sent, or imagined reaching. There is something in this that the mind returns to in quiet moments. Not a frightening thought necessarily, more of a grounding one. The universe is not small. The solar system is not small. The place you are born into, the gravitational territory to which every atom of your body technically belongs, extends in every direction to distances that make the word vast feel insufficient. You live in the innermost room of an enormous structure, and the other rooms are dark and cold and old beyond any frame of reference ordinary life provides. The objects in the outer Oort cloud have been orbiting since before the Earth had an ocean, since before the moon was formed, since before any biological life existed anywhere on this planet or, as far as we know, anywhere else. They have circled the sun slowly, in that enormous cold through the entire history of life on Earth, through the Cambrian explosion, through the age of the dinosaurs, through every ice age and every warm period and every mass extinction and every evolutionary transition that produced the organisms alive today. Through all of that, they have simply continued orbiting, patient in the way that only cold and distance and vast time can produce. And they will continue after this civilization, after this species, after the particular arrangement of matter that constitutes your body has long since dispersed back into the elements. The outer Oort cloud will still be there, orbiting a sun that will have aged considerably by then, in the same cold and the same dark, the same slow drift around a star that will no longer be exactly the star it is tonight. This is not a sorrowful thought, or it does not have to be. It can be held another way, as a reminder that the solar system is larger and older and more patient than anything human, and that being part of it, even for a brief and barely perceptible time, is not nothing. You are made of material that formed in this solar system 4.5 billion years ago. Some of the atoms in your body may have, at some early point, been part of objects that were flung outward toward the Oort cloud, before eventually finding their way inward again and into the chemistry of the early Earth. You are, in this sense, not just a product of the inner solar system. You are a product of the whole thing. The planets and the Kuiper Belt and the Oort cloud and the interstellar material that drifted through before the sun formed. All of it. The entire structure, from the blazing center to the outermost cold. It is all one thing in the end. One gravitational family, extending in every direction, connected by forces too faint to feel, but real enough to hold 1 trillion frozen worlds in slow and ancient orbits. One system, vast and quiet and old and mostly dark, with a small warm light at the center, around which, on one unremarkable rocky planet, something improbable happened. Matter organized itself in such a way that it could look outward, measure the distances, infer the structure it could not see, and sit quietly with the understanding of how large the home it had been born into actually was. The Oort cloud is the outermost expression of that home, the part of it that has never been touched by anything human, never been lit by anything but the faintest starlight, never been visited by anything warmer than the cosmic background radiation of the universe itself. And it surrounds you, right now, in every direction, at distances measured in light years, in the cold just above absolute zero, in the ancient dark beyond everything the diagrams ever showed you. That is the scale. That is what was always out there, beyond the poster on the classroom wall, beyond the neat rings of planets, beyond the comfortable edge that the diagrams drew for convenience and the universe never recognized. The solar system does not end at Neptune. It does not end at the Kuiper Belt. It does not end at the heliopause. It fades slowly across distances that swallow centuries of travel time, through 1 trillion objects none of us has ever seen, into the space between stars. And the space between stars is itself not empty, but populated by the outermost remnants of other systems, other histories, other collections of frozen material orbiting other stars in their own slow and patient dark. You are part of something much larger than the diagram suggested. You always were. You are listening to these words from somewhere inside the innermost fraction of the solar system. A warm planet, a breathable atmosphere, a surface tempered enough to hold liquid water and the chemistry that water makes possible. You are, by any cosmic measure, in the most sheltered and improbable part of a vast and mostly cold structure. The warmth you feel, the light coming through whatever window is nearby, the sounds of whatever world surrounds you, all of it exists inside a tiny region at the center of something that extends, in every direction, nearly 2 light years into the dark. The Oort Cloud does not care, in the sense that cold and ancient things cannot care. It does not know you are here. It does not know anything. It simply orbits, a trillion frozen objects in the slow, patient dark, carrying 4 billion-year-old ice, each one alone, each one part of the same family as this warm planet, connected by gravity, too faint to feel. The scale is hard to believe. That is true. It was always true. The human mind did not evolve to hold distances measured in light years, or timescales measured in geological epochs, or populations measured in the trillions. The mind evolved for the immediate world, the savanna, the horizon, the faces of people nearby. The Oort Cloud is not nearby. It is about as far from nearby as anything in the solar system can be, and yet it is ours. The same sun that rises every morning over this planet extends its gravity, thinned almost to nothing, across a distance that makes the planets feel like a warm room. The same solar system that produced this world and every living thing on it also produced the cold shell surrounding it, the frozen archive of its own violent origin, stored in the dark at the egg of everything. Walk outside tonight if you can. Look at the sky. The stars you see are not the edge of things. They are neighbors, each surrounded by their own vast and invisible halos, their own collections of ancient cold. The space between those points of light is not empty. It is old and full in ways that instruments are only beginning to suggest. And somewhere in the dark, beyond everything visible, past the reach of any probe or telescope or signal yet sent, 1 trillion objects drift in silence around the same star that lights your world. They have been there since the beginning. They will be there long after. The solar system is larger than the diagram. It was always larger than the diagram. And the outermost edge of it, the part that fades toward the stars, cold and unreachable and real, is as much yours as the ground beneath your feet. You just cannot feel it from here.